Hey guys, welcome back. So in the last video, we ended right on this slide when we showed how to derive a likelihood using the IID assumption that allows us to work with up to n different observations at the same time. Then we said, okay, well, if I'm being a frequentist, I'm going to maximize that log likelihood with respect to the parameter, and that one value is going to be my maximum likelihood estimate. So Bayesians approach the world slightly differently, although I hope by the end of the lecture to show you that it's only slightly so. Bayesians say there exists a posterior distribution. It's a distribution of the parameter given an exact data set. And here is the form of that posterior distribution. And we will spend a little bit of time showing exactly why that's the case. Why, when we take the likelihood, multiply it by the prior, and divide by the average likelihood, also called the marginal likelihood, we get the posterior distribution, or the distribution of our parameter given our data set. Now, once we get this magical distribution, we can take its mean, its median, 25th percentile, interquartile range, maximum, minimum, to get at, okay, well, here is the range of plausible values. What is the most plausible value? Well, that's the mode. What's a typical value of the parameter? Well, that's the median. And so there's a lot of things we can do with this posterior distribution once we get its mathematical form. So I always thought it was cool that Reverend Thomas, who was Italian, Bayes, in 1763, verbally stated the now famous Bayes rule that allows us to write the posterior like that. So to be clear, this is our prior. This is our likelihood, not log likelihood, but the likelihood. This is the marginal distribution, and I'll explain what that is. And this, of course, is the posterior of theta. Why? Why are we allowed to do this? Well, let's play a bit with Reverend Bayes' theorem. So from introductory to statistics class, your instructor, would have been me, may have said something like probability of A given B can be written as the probability of A and B divided by the probability of B. When I teach, I say this vertical line, which is the conditional on the given line, turns and becomes the division line. Okay. So to start our games, we will say, all right, I'm going to start with the matching up the likelihood. So I will assign y to be A and theta to be B. So here is our likelihood. Sometimes it's written in terms of P, sometimes it's written in terms of F. And according to our intro to stats Bayes rule, this is the probability of both y and theta. So this is called the joint distribution, by the way. The joint, simultaneous distribution of our data and our parameter. Right? This is the distribution of data given a certain parameter. This is the joint distribution of data and the parameter. All right, and then just following our rule, these are the distribution of our parameter without the data. So this is the prior, right? All I have to do right now is multiply both sides by our prior, and I get the following. I can take my joint distribution and I can rewrite it just like this. Now, this is immensely helpful because we never observe or talk about the joint distribution. The distribution of two unknowns, the data and the parameter, what is that? You know, we spend a lot of time talking about the likelihood. We talk about, in regression class, we talk about approximate normality. For example, you can take your data, make a histogram, and suppose that your likelihood has a normal distribution or a log normal distribution or a gamma distribution. Point is, we talk a lot about the likelihood. In this class, we spent some time talking about priors, uninformative, informative, weakly informative, proper and improper. But the joint distribution, I wouldn't even know where to begin. And so this, being able to write the joint distribution of our data and the parameter as a product of the likelihood and the prior is immensely powerful. Because this joint distribution helps us derive our key quantity, which is the posterior. Okay, so we're going to use this result in a second. I have to insert a new slide. Okay. We're still going to refer to our intro to stat Bayes rule, but I'm going to start at a different point than here. I'm going to start with what I want to find, which is the posterior. I want to find the distribution or the probability of theta given the data. That's the posterior. That's the quantity I'm trying to derive. Applying my introductory Bayes rule, right? I need the joint divided by, right? I need the joint. Talking about joints, I know. I need the joint distribution, okay? This given sign flips, becomes a division. There's the prior, right? This is the joint. This is the prior. Am I there yet? I'm close. Because according to my previous result, I can rewrite the joint distribution as a product of the likelihood and the prior. I'm sorry, I made a typo. I made a typo. If we were in person, you would be screaming at me that we made a typo. Y goes here. I'm so sorry. No harm, no foul. All right. Marginal of Y. Okay. We're almost there because according to our previous result, I can rewrite the joint as the likelihood times the prior. And so we get the expression we were going for. This is the likelihood that we all know and love. These are the priors that we get to set and think about how informative, uninformative, weakly informative we want to be. We typically go for proper priors. And now it's worth it to kind of take a quick look at this oddball quantity, which is the marginal distribution of Y. So moving on to this next slide. The marginal distribution of Y, the average likelihood, that is, we average Y over all possible values of the parameter, is typically what is called expensive to compute because we have to integrate. Integration is hard whether you're doing it by hand or you're making a computer do it. So we have to go back to MathStat. And so from kind of first principles, if we have a joint of X and Y, from first principles here, And now I was looking for the distribution of x. Find the marginal distribution of x. I would say, okay, the marginal of x, I have to integrate y out. Integrate over all the possible values of y. Integrate what? Integrate the joint with respect to y. So for those for whom calculus was a little while ago, this notation right here, this is the joint distribution of both x and y. This is the integral. An integral is a type of average. So if you're thinking about it, I have a plane. I have a plane. And this plane, I can integrate in this direction or in this direction. And depending on which direction I choose to average in, I am left with either a distribution of x or a distribution of y. So notice that I can go from joint to marginal. This is the marginal of x. And then, of course, if you're following along, if I integrate now in the direction of x, integrate what? Integrate the joint distribution with respect to x, I get the marginal of y. So there's a key here, and that is integrating theta out. So if we go back to our Bayesian world, I don't have x and y, I have my data y, my observed vector of observations y, and I have my parameters, theta. In this case, in the first case, is just a single parameter. In the second case, I have a bunch of parameters, k parameters. So to get my marginal of y, I integrate the joint distribution with respect to theta, or say over theta, and I get something that is a distribution of y. One key here, the marginal only depends on y, not on theta. This might be an obvious thing to say, right? Just by the sake of mathematical notation. This is just a function of y. It is no longer a function of y and theta. It is definitely not a function of theta, right? If we go back to the posterior is a function of theta given a specific y. So y is actually a constant here, and theta is the variable. So we're working with this denominator down here. The thing is, the denominator down here does not depend on theta. And the posterior is a function of theta. And so this altogether allows us to simplify the expression a bit further. I'll go back to the case with several parameters in a sec. It's mostly just as an FYI. But because this average likelihood, the marginal likelihood, does not depend on theta, you can say it's like a constant that is a function of y. We can write and use this proportional to symbol that you see being used sometimes when people talk about Bayesian statistics. So remember that we started with this. Right, here's the likelihood times the priors divided by the marginal. That marginal distribution is the result of I don't mind rewriting it actually, because you will see it again and again and again out there in literature, is a result of integrating out theta. When you integrate a variable out, it's no longer a variable. And so then the result in a denominator is a constant that does not depend on theta, right? It's a constant that only depends on y. And so what you can write then is you can use the proportional sign. You can drop the constant that is not affecting theta, and you can instead just use the proportional to sign. Okay? So the key here is that the marginal distribution does not affect the shape of the posterior. What you divide by here does not affect the shape of the posterior, because the posterior is, again, a function of the parameter. It's a function of the parameter. It does not affect the relative frequencies of thetas inside the posterior. It does not make certain thetas more likely than others. And that is why we can use this proportional to sign. We really like not having to compute our marginal distribution. Because in the case of a single theta, you can say, well, there are numeric integrators. There are plenty of numeric integrators that will allow me to programmatically evaluate this integral, and you would be correct. There are plenty of numeric integrators. But in a typical regression analysis, in your regression class, when was the last time that you only had a model with a single parameter? The answer is never. Because even if you have an intercept, you still have the error variance sigma squared. So even in the simplest possible regression model, you have at least two parameters. And quite often, you have many parameters. So in reality, that integral is looking much more like this. So to find the marginal of y, you would need to perform a k-dimensional integral. Now recall, I have a little bit of notational trickery. According to a result we earlier had, I can rewrite the joint distribution as the product of a likelihood and my priors. I'm just rewriting the joint according to this result. According to my first result, I can rewrite the joint distribution as the product of a likelihood and my priors. And so, as I come back here, that means that if, as is very often the case, my likelihood depends on several parameters, I'll make my y a vector, as is always the case. And now this depends on, say, two parameters. I would have something that looks like this. And now I would have to integrate over both theta 1, excuse me, and theta 2. D theta, I guess 2, d theta 1. And that's for two parameters. But again, think back to your regression class. Think back to the last regression that you saw in a publication. Had a lot more than two. So the complexity of this integral, if you're trying to compute the true posterior, not just what the posterior is proportional to. If you're trying to compute the true posterior, this integral becomes expensive, becomes difficult and onerous to compute very quickly. That's why, for computational purposes, we're going to be sticking to almost always something that looks like this. Posterior being proportional to our likelihood times a prior. So remember I said the entirety of frequentist analysis is contained inside the likelihood. Well, now I'm saying we actually don't need to worry that much about this average likelihood business. We're just scaling. Our posterior is proportional to a scaled version of the likelihood. Wow, that's not so scary. And really, we just learned about log likelihoods. And so what this means is, if the posterior is proportional to the likelihood times the prior, what actually happens behind the scenes in software is on the logarithmic scale. And so if we take the natural log of the posterior, right, you take in the natural log of this product. The log of a product is the sum of logs. So you're actually going to be proportional to the log likelihood plus log priors. So now remember, the log likelihood is what we maximized to get our frequentist estimate. And to get our posterior distribution, our log posterior distribution, we simply take the log likelihood, add our log priors, and that surface that is a function of the parameter is what our posterior is proportional to. Proportional to. So now I'm back to this slide that I know I covered before, but it's a good time to revisit it. So if my prior has very little information, in fact, this right here really is a true uninformative prior. All values, this looks like probability. This is theta is probably a proportion here. So if my prior has very little information, and by the way, we're operating right up here now. Those pictures are using this multiplicative form. If my prior has very little information, then my posterior is just going to be a scaled version of the likelihood. That's all, right? This is proportional to. If my prior bakes in a hard bound, it doesn't matter what I observe, that hard bound is going to also appear in the posterior. Look, over here we're multiplying by 0, right? So anything multiplied by 0 is 0. So if you a priori assume that something is impossible, that means in the posterior, it too will be impossible regardless of the data you observe. And then finally, the shape of the prior. The shape of the prior. In this case, it has this interesting wave shape. You can see that it's actually propagated into the posterior. So this point up here, a discontinuity perhaps, in fact, almost certainly a discontinuity, gets propagated into the posterior. So issues with your prior, something like a discontinuity, will be propagated into the posterior. Here is a more realistic, less contrived case of a weak prior and a strong prior. And what I will say about weak priors and strong priors, we must keep the scale of the data in mind. So far, we've been flipping coins, right? And theta is the probability of a head. So the left-hand side is certainly a weak prior because it's so, you're allowing for the possibility, a non-trivial possibility, that the probability of a head will be less than 0.2. You're also allowing for an equally non-trivial possibility that the probability of a head will be greater than 0.8. Both of these indicate you believe it is possible that your coin could be biased, right? An unbiased coin, of course, is right around 0.5. Well, this weak prior is centered at 0.5. So you're saying, well, before seeing data, I'm going to make 0.5 my most likely a priori value. But I'm going to bake in quite a bit of uncertainty into that prior. And I will allow for the fact that my coin can produce heads with probability of less than 0.2 and with probability of greater than 0.8. In some ways, it's kind of a silly prior, but hey, you don't know. I was flipping the Susan B. Anthony dollar. I don't know anything about the Susan B. Anthony dollar. Nothing about it. So maybe a weak prior is more appropriate. So in the presence of this weak prior, you can see that the posterior distribution is far more alike to the likelihood, but not identical. Even with a weak prior, we see that there's a bit of movement, right? You think about where the mean, or you think about where the typical value is, the median value inside that posterior, I bet it would be somewhere over here. There's the median of the posterior. Not the median of the data, the median of the posterior. Call it like 0.7. The maximum likelihood estimate would be the value that maximizes our likelihood. In fact, we derive the fact that it's just the average. And this is 9 observed heads from 10 coin flips. So the maximum likelihood estimate is 0.9. That's not incorrect. That's what you observed, right? In a frequentist analysis, you're only using the likelihood. And your likelihood says the maximum likelihood estimate, the value of theta that maximizes the data observed, is theta hat equals 0.9. Even with a weak prior, your typical probability of heads is less than 0.9. Let's see what happens with a strong prior. You don't know anything about coins, but if you grab a coin, you look at both sides, there's not something weird happening where there's a weird shape where you maybe like kind of hold it in your hand, you look at it. Maybe you use your prior experience with coins. You use your prior experience with flipping coins. I know, all those times in your life when you had to flip a coin. And you're saying, you know, I really want to assign quite a bit of prior probability around 0.5. In fact, you know, I don't know anything about the Susan B. Anthony dollar, but boy, would I be surprised if it was anything, the probability of heads in a Susan B. Anthony dollar would be anything less than 0.4, or anything greater than 0.6. Sure, it could be 0.55. It's not exactly fair, but man, I really don't think, a priori, really don't think it's less than 0.4. Really don't think it's greater than 0.6. Then look, it doesn't matter what we observed. The posterior distribution, the blue curve here, really favors the prior with a sample size of only 10. As the sample size increases, we would start to see this start to creep closer and closer towards the likelihood. But with a sample size of 10, in this silly example, your data are not enough to overpower your prior. So there is a little definition here, and you may have heard this term before. On the left-hand side, we say that the data dominates. The data dominates the prior. On the right-hand side, we say it's the prior that dominates. And it all depends on your sample size, how strong your prior is, and of course, the scale of the data. So on Thursday in our class, I will go through our first R example. I will go through and we will visualize and make some posterior distributions. So thank you so much for your attention today. I know there was a lot of material. Do see me during office hours if you have any questions, and have yourselves a great night. Thank you so much.